thank you for the introduction. I'm glad to present you the paper Design with Industry 4.0, Priorization of Sensor Data for a Smart Data-Driven Product Development Process. By myself, Tobias Stürmlinger, and my colleagues from the Institute of Product Engineering at the KIT, Bartosz, Gladysz, Markus, Strauch, and Albers. So after giving a short introduction and motivation of the work, for the methodology we used in this case, and then we applied it to a real test case with project partners in a funded project, and then I'll give you a conclusion and outlook. So nowadays Industry 4.0 is in everyone's mind, and there's a lot of research and projects regarding this, but most times it focuses on typical production issues like how to reduce waste, how to increase flexibility or connect with machines and stuff like that. But we recognize that there's also a demand for people who are developing products or production systems to think about how can we use the data that is created with Industry 4.0 in our production, in our development process. Furthermore, the collaboration between companies and their customers, no matter if it's B2C or B2B, is increasing because in the whole value chain there's a lot of data, and it's more getting individual products and so on. So this is also a part that's important in this case. And what's an issue is that there's no methodology to support the product developers to identify the potentials of Industry 4.0s in their production process. So they know, okay, we want to collect a lot of data, but the question is, what is the right one we need and what to do with it? There's recent research, for example, at the RWTH Aachen, where they look for different research challenges in product development regarding data from Industry 4.0. So they made up this matrix with the 8 cells, where they looked for the product or for the process in different challenges. But within these fields, there's a lack of methods that support the engineer, the product developers in their work to deal with the data for, in case of Industry 4.0. So what we did is doing research in a funded project directly with a small, medium-sized company that is producing or developing production systems by using the data of one of its customers. First of all, we set up a framework here. This is a string coiling machine by WAFIOS. It's our project partner, and right now they are developing the next generation of their production system, and they have already a production system at their customer here on the left side, and we have a generalized production development process. And now it's important to identify how can we support them by using the data from the machine that's already used. So we have a lot of data getting out of the machine, sensor data that's from sensors that are already implemented in the machine, or from sensors we additionally applied in the production process. And then they get out different kind of data sets. For example, they get the performance and the load of the machine by measuring the torque of the different engines, for example, or the NC axis. Then of course they get the quality data out of the production process. So they measure with a camera system, for example. In this case it's a string coiling machine. They can measure the diameter and the length of springs. So this is also an important database. Or last but not least, the feedback of the machine operator. Because he can give feedback of how the machine worked. Was it easy for him to use it, but you also can give, this is kind of a subjective feedback. You can also give objective feedback by, for example, giving us reasons why the machine stopped. So because he had to change a tool, because the tool broke, or just because he did a lunch break or something. So that's all data we have. It's very important to understand that we're thinking in product generations here, because the developer of the production system is not just developing his system on a white paper, but he uses his reference system, the system that is already in use at his customer, and of course he's using this data to improve or to vary this production system. Furthermore, we used the integrated product engineering model from our institute, where we have a generalized product development process. It shows different activities and in the product development process, and different steps of product solving. And so in this model, we could analyze our project partner's development process and see in which of the product development activities we can support him with the data given from the production. So this is our methodology. First of all, we identify the data sources. I already talked about it in the last slide. Then we looked at the different activities in this product development process, and then we established an engineering potential matrix where we looked in which of the activities can we support him with what kind of method, how useful is it for the product developer, but also what kind of data do we need to support him in this case, in which level of detail. And then we could get in discussion with his customer that's using the production machine if we are allowed to share this data, or if we have to alienate it, or sample it down to characteristic factors, for example. So this is a closer look at the product development process. We looked at the different activities, and then we clarified for which activity which data can be an input in our product development activities, or out of which activity, maybe in our case from the previous activity, do we need to get data out to develop or to feed the database. The engineering potential matrix looks like this. So we generalized the product development process and made it especially for the needs of our project partner. And then we looked how much data do we need to support him in the different possible and different possibilities. And then we have different influence values that can help us to support him in those different topics. So you can see how useful is it for the project partner, but also if we see we need a lot of sensor data, a lot of machine data and so on in a high level of detail, we also know it's getting very complex to support him with a method or with a tool. So we could think about, is it even possible in this terminated project, or we can give him a hint what he can do after the project with this data. So in the test case, like I've already said, it's a spring coiling machine, and especially we've seen that in detecting product profiles, so in, for example, detecting what his customer really needs or what the customer does with the machine, we can use the different data sets very intensely. Because of the time, I won't get in very detail here. I'd like to describe the test setup a little. This is the center of a coiling machine. We have the wire getting fed in here, and it's getting coiled from the first coiling tool. Then it gets turned around by the second coiling tool, and in the end there's a cutting tool cutting the wire, so we got our single spring. Additionally to the sensors we already have in the machine, like a camera system for the quality measurement, or for example the measurement of the torque of the wire feed, we implemented a thermocouple at the coiling tool, piezo force sensor to measure the forces we have here, and an acoustic emission sensor. So we hope to get information about the tool wear, about the different tools in the production system. This is the final engineering potential matrix we worked out in 2 expert workshops with our project partners. In the top left, we defined with them kind of overall development goals they have in their company. So they are interested in the machine controller for their project partners. So it's easier for its customers to control the machine, or to find the right parameter set for the different springs. But they are also very interested in improving the different tools or engines they have in their production system, because those are the parts that have to be changed if it's damaged. It takes a lot of time, downtimes, costs for its customers. So if you improve that, you will get a big benefit for your customer, and then of course for your own company. So we've seen, for example, that it would be very nice for them to have a virtual spring model to improve those machine parameters, but we see that there's a lot of data you need to implement something like this, because it's not enough to make experiments with just one type of spring. You need to do it in the series production with a lot of springs, and the even harder part is you really have to understand the physics that's behind the whole forming process. So it's not enough to do a statistical analysis of the data you get. You really need to understand what happens. So we discussed that at least in this project, it's not realistic to set something up like this. But we also discussed that by implementing damage models of the coiling and the cutting tools, it helps them a lot to understand more about their tools, and maybe to implement predictive maintenance stuff, or even by saying, okay, I see my tool is breaking then and then, so they could rethink in their next product generation how to dimension the tool. If they maybe use another material, or they make it bigger or smaller, or something like that. And even for the engines, we can't say anything about the engines by having a damage model of the coiling and the wire cutter, but we can use those models as a basis to develop a model for the engines as well, because it's based on the same, can be based on the same kind of statistical analysis. So in the end, we've seen the data that we need of the different sensor and machines is a lot less complex than, for example, for the virtual spring model, why we agreed with our project partner to implement such a damage tool. So to implement it, it's very important to classify the wear of the tools, and the main problem is that it's very subjective. So if you get out one of those tools of the machine, one worker would say, that's quite good, I put it back in, and the other one would say, oh no, I don't want to produce a spring with this anymore. So we define 4 different classes in order, and that it's broken, that's quite obvious. Or not in order, it's a new one. And the other 3 classes are classified by the state of the spring. So we assume that if there's a surface damage or shape deviation of the spring, there has to be a problem with this coiling tool. Of course, there are other influence values, but this is the main issue. And then we use all of these data that we have, machine data, sensor data, condense them to characteristic factors, include the customers or the machine operators' feedback, and then we can do different classifications or regressions to do to develop the tool-aware model. So, in the conclusion, we conducted 2 expert workshops with both the developer of the production system and its customer who's producing the springs. So they got a clear overview of the activities where they really can use the data out of their customers, and they can prioritize which tasks to do. And what's also really very important is that both of the partners get a common understanding which data is really nice to share, and then can get agreements on how to deal with these issues. And yeah, in future, they also want to set up a kind of cloud to collect the data from their different partners, and there this can also help to approach them by telling them, hey, this is the data we need for this and this task. Can we have it, or find solutions how to alienate the data, for example. And yeah, based on that, we made definition of test series in the production that are running right now for implementing that WARE tool. And in future, it's important to check the transferability to use the data for other methods and tools. Of course, this was kind of the methodology background, but you have to see how it works when you really implement the tool, what we do right now. Yeah, that's the end. Thanks for your attention, and I'm hoping to get some questions in the end.